So, good afternoon again. My name is Francesco. I come from Maresis, which is a spin-off of Technical School of Milan. And we'll have practicals now, so we start to get into deep with some coding and some examples into the theory that you have seen today. Before we start, so if you're cold, we can close the windows, so just tell us. And if you have issues with the Wi-Fi connection, there is people from University of Ljubljana supporting. And if you have instead problem with the platform or the application, we have Joseph over there, Saskia over there, and Janka over there. Thank you. So before we start, I don't know if you've already taken a look. So you should be logged in with your account into the map. There is this shared bucket, and the information was given to you by email. Which has an address and has all the files inside. So I suggest, if you take a look also here at the screen, I suggest you copy the notebooks and this Nagoya JPEG and the common functions into your home or into a subfolder of your home. So the first time you make your access to the map, it gets some time for loading. Just don't be worried about it. If it's too much, more than I would say a couple of minutes, then please call Saskia or Joseph. I will show again, just to the benefit of everybody. So when you're in your home, you have folder share buckets. And then it's this one. So EE003 blah, blah, blah. Then inside, you have advanced course, and then first one. So that's the path. So there is the path, and then the 4 files that you need are just these 4 highlighted. So you don't need to copy all the content on the folder. Because in the notebooks, we are then changing the paths, and we will point to these files, which are quite big. Is anybody able to access their home? Are you? OK. Then the next step is entering here. And then if you sort by name, it's this folder here. Okay, you see also the full path there. Then you go in. And look for the first one. Yeah, sure. Yeah. You just need to do like this, copy, and then in your home folder, you can create a folder, put it there, or just put it in the home. Your home, like here, if this folder, home Jovian, is your home. Everybody has the same name. Let's try to get started. So once you copy the files, for me it's just this folder here, we're going to need the SAR TomoSAR 1, part 1. And the first thing to do is that the second cell you see, you should change the path. So to this one. So it's pointing to the folder in the share bucket. Otherwise, it won't read the data. And you'll also have to, so I just instantiated a variable here. You have to sum this to the relative path. So since many of you had this problem, let's say in the very first cell, So hopefully, I wanted to have you interactive plots. Unfortunately, it's not working on this platform. So since some of you had problems, I suggest you just maybe delete these lines here, the widget stuff. So no interactive plotting. We will play with the arrays a little bit more. And eventually, you can also uncomment this line. And I suggest you all do this, because some of you had problems with that. So a couple of things more. So also in a later cell, you find a line for interactive plotting, which is uncommented in your notebook, this one. I suggest you delete it or comment it, because otherwise it will switch on again the interactive stuff. But unfortunately, it doesn't work here on the map. So, and another point, when you put the full path, it has to be the full path to each file. So you can either specify the whole string for each of the three, or you'll have to define a common part and then sum the strings, like here. And a common part should have home Jovian as a start, because it should be an absolute path. So some of you forgot the first part and it doesn't work. Okay, so let's start. So what we are doing today, well, just a few introductory notes that you will hear more of in the next days. And then we will start looking at a single image per se and polarimetrically. And later on, there will be also something on tomography. So just a few introductory notes. So I've written a lot of notes here and there, no? Also for you, that you can review later. So biomass dataset, there's an official catalog, which is also called Map Explorer. You have to create an account, but if you have created an account for the map, I guess it's the same. You log in. It has a graphical interface. You can specify dates, level of products, level of processing, a lot of stuff. And then you fill in a bucket, and then you download the products. So you have a couple of links here. This will be explained more in detail also in another lesson, I guess, on Thursday. So you will probably have actually an interactive training on Thursday in which you will try to download yourself the data from the map and process them. So the data we're interested in for today, it's two types of data. So we have level 1A data, which is the single images. Focused, it means with the synthetic aperture processing already done. Also calibrated, so in theory, so this mission is evolving very fast, right? But a lot of people did a lot of work in the last months, so these images should be calibrated as for radiometry. And also have some disturbance removed. No? There has been some ionospheric processing, for instance. Removing some of the distortions. Polarimetry is also supposed to be calibrated. And then you have level 1C. So we skip level 1B is something a bit different. It's just amplitude. It's already put on a map, but we are not interested in this level of data here. Level 1C is instead there is a single image. I mean the product, one level 1C is one image. But these images belong to a stack. So you have, as you heard this morning from Stefano, either 7 images nominally. It may be even 8 or 6. It depends if the radar was able to collect more or had a failure. For a tomographic stack, which is what is being acquired in this very moment, and it will be acquired until beginning of next year. For the rest of the mission, you will have typically 3 images, so dual baseline configuration. Again, can be 2, can be 4, maybe. So the level 1A suits a lot of purposes. The level 1C is actually level 1A, which has been additionally co-registered, so it means that all the images are put on the same grid. No? Usually you choose one for the reference, and you align all the other images to that one. and has more processing behind, because since these images are interferometric, they have a further interferometric calibration, which is especially useful to give you a clean phase. So again, ionosphere is the main source of corruption here, and these are finally calibrated also to compensate ionosphere at the interferometric level, plus some other processing. We don't need to go too far with this now. You also have a third link, so actually all the people working on the algorithms are basically feeding one common framework, so which is the one of the operational processor, basically. It has been initially and foremost, first and foremost, developed for the ground segment, processing the data that are actually stored on the catalog later on. But ESA has decided to open this to the community. So you have this website in which you find the source code of the official processor. It's a bit of a complex machine, so maybe it's not so straightforward for newcomers. But I know, actually, if you go back to the home folder for a while, maybe later, you don't have to do this now, you have a folder called the BPS, Biomass Processing Suite. So the idea is to put it on the map, and maybe in time there will be some template or wrapper or something that can put you in a better position to use it. Usually the processors have a lot of configuration files, you have to know the product formats, a lot of information. But so you have the link, so you just know. So maybe you will see this more in detail Thursday, the structure of level 1 products. So level 1A and level 1C is actually pretty similar in the sense that you have a product is a folder, no, with a specific naming, and then you have subfolders. And inside each of these subfolders, you have different things which make the data, the auxiliary information, and also a preview of the data. So let's say level 1A and level 1C are pretty similar. Again, they have maybe different annotations, but let's say the data content is really similar, and the folder structure is the same. So here is an example from a level 1A file. So you have the naming is quite long, it has a lot of things. So you have bio stands for biomass, of course. S1 indicates the first subswot, because in biomass you have 3 strips covering, let's say, different patches on nearby areas, a bit overlapping, and each of those has a different incidence angle. So each of these is about 50 kilometers on ground in range. In azimuth is 150, and so all the 3 together make more or less 150 by 150 square kilometers on ground. Then you have dates, a couple of strings for dates. You have basically the start and stop of the acquisition time up to seconds. Then you have just one letter. T stands for tom phase. If it was commissioning phase, it would be C or com, I don't remember. And interferometric phase will have an I, probably. And then you have a series of other strings like G, M, C, T. These you can look up if you're interested in the documents at the link above. They basically identify which place you are acquiring. So G is the global cycle, M is the major cycle, so it means which run of the world you are passing over. Specifically which swath, which track, which frame, which portion of azimuth, so you have all this information. And then at the very end you have just a code made by letters, which identifies basically the batch of processing that generated the product. So each product generation, even starting from the same raw data from the start, has a different ID. So the folders, you have different subfolders. So typically inside the main folder you have just the subfolders and an XML file which has some annotation at a very high level. And then you have to go into the subfolders to find the quantities. So the most important is of course the measurement one. In the measurement one you have the actual data. And the data are stored in a couple of files. The format is GeoTIFF, which is quite standard. So it's a binary raster plus some header, let's say. You have two files because complex data are stored in two separate files. One is for the absolute value and the other one is for the phase. So the processor, for instance, has a reading routine that knows this and plugs these two files back together. But I guess also, maybe Saskia, I don't know where you are, correct me if, okay, she's outside. Maybe on Thursday you will see, I think Saskia may have prepared some reading routine doing this for you. Otherwise, the good thing of having, of course, let's say official tools should be conceived to ease your life because they were coded according to the formats. But otherwise, it's standard formats. So you can also read those with Python, several libraries, let's say, or even other software. Then you have the annotation folder, which is also very important. Inside this folder, you have typically a netcdf file that has all the lookup table stored into it. Lookup tables means you have all the information about geometry and data location. So usually you have rasters coded into the netcdf, which represent the digital elevation model that was used to process the images. In the case of level 1C, for instance, since they are interferometric images, you also have interferometric wave number map. So if you remember this morning, it's the, let's say, the magic number that converts a height to a phase. You have also latitude and longitude, which correspond to the coordinates of the digital elevation model that was used to process the data. In the case of tomography, this does not hold for all the pixels that you retrieve with tomography and elevation because they are at a different height. You know? And if you remember, the radar sees like this. So you'd have to update this information. And let's say the part of the official processing that is being developed will account for that. So it's all stored in a netcdf, so you have the lookup tables themselves and you have also their axis, which is important, also measurement unit and so on, because usually this information is downsampled with respect to the actual data because it's at coarse resolution, so to save some space. Then you have a specific navigation subfolder which contains information about orbit and attitude of the platform. Then you have two more folders, basically. The schema one is not very important for you. It's just, let's say, how the XML annotations are coded. No, it's just the schema of the XML. Oh, I forgot to say that in the annotation one, you also have actually an XML which contains a lot of important information, actually, like the resolution, the sampling step, I don't know, the polarization of the radar, all the information about the sensor and the acquisition, and also the processing. You have the processing history that brought you to that product level. So in the case of level 1A, for instance, you'll have annotated whether RFI correction was applied or not, whether ionospheric correction was applied or not, which parameters, and so on and so forth. And then maybe the last folder is the preview one. The preview one is just a KML file plus a polarimetric quick look. Quick look just means a very coarse version of the amplitude image, so very averaged, smoothed, and downsampled. If you double click, this brings you to Google Earth and you can visualize on the Earth. So this is just a very, very quick wrapper, but again, you'll see more of this. You can go back to the notes later. You'll see hopefully more of this on Thursday probably. And just a couple of notes. So for these tutorials of today, we have prepared and saved the data in NumPy format because it's handier. Otherwise, we'd have to go through downloading the data from the catalog, installing the BPS or whatever, reading the data, so it would have been probably more lengthy. And not a number values are replaced with zeros, which is not always the best choice. So usually in an image you have non-valid values which are coded with a special number like minus 9999. For this tutorial we have just put a 0 in the data and not also like a NumPy, not a number value, because we use some functions that do FFT. and they're a bit misled by these values otherwise. Also, okay, no, well, let's just go like this. So let's get started. So first thing first, I would say SAR and multi-look. So now we'll load one image, just one, all polarization, and we'll just take a look at this image and see how it is like that, how it is by doing a bit of multi-looking, a bit of smoothing, and then polarimetry also. So the first cell, I think I would do like this probably. I suggest you do the same. So just delete the couple of lines that activate the interactive widget because it doesn't work, unfortunately. And just to be on the safe side, uncomment this line. So you have static plotting. Otherwise, you can run it. It's just an import of NumPy, basic algebra with Python, matplotlib plotting, and a couple of functions that I prepared and are contained in the common function file. But one is for plotting, so we don't even need to speak about that. The other one is for multi-looking, and we will speak about that when we come to the right cell, let's say. So I guess you're okay with the paths. So here you basically specify just the path for the three polarizations. It's a separate file for each. Here it's called a stack, but it's just one image. We will see we have more than one in the tomography practical. And we just define, this is contained in biomass data in the metadata, the sampling steps in meters, in slant range and azimuth. And this is a slightly lower value than resolution. Usually you don't want to sample your radar data at your resolution because of, let's say, mathematical problems connected to digital data. So this number usually is a little bit slower, at least, a little bit lower, sorry, than the actual resolution. So say the range one is 25 meters, then you would sample at 20 meters, more or less. Huh? So you can also, I think, run this cell quite safely. And then, okay, so it takes maybe a while. Okay, so plotting. So the inline instruction is okay. Maybe I suggest, since we'll have to slice the array ourselves to make a zoom, because the interactive plotting doesn't work, I suggest maybe you comment this line here, which removes the axis, so you can read the number of the pixels. And also maybe, let me see, here we're not putting axis in the plot. Also, let's say, for the sake of consistency, you can comment also the labels, because the plot we are doing is not actually in kilometers here, but it's just in pixels. So if you run this cell, as you see, it's just computing the logarithmic version of the absolute value squared, which is the intensity. It's somehow connected to the power of the data. It's not actually power, because usually the data are converted to digital numbers. It means the quantity is relatively linked to physical values, but it's not actual, I don't know, voltage or stuff like that. So if you run this line, well, the warning is just because we have zeros, and of course we are taking the log version. This plots the dB version of HH intensity as it is. No, this is the entire scene, and this is a scene from Nagoya, Japan. So you already start to see there are different type of land covers. No. And okay, the next cell is for the crop. So also here maybe, well, it's not really important that we comment the axis. Let me just check everything is okay, so we don't put physical labels also here. We just replace the small values for not having warnings. So if you run this, you see a zoom. And the zoom, it was just taken from, I don't know, the first 1,500 lines, more or less. So maybe we can take actually, we can rerun this another time if you wish. We can take maybe, I don't know, let's make it 1,000. A closer zoom. No? Okay, this is a very annoying thing. Maybe data types in Python are quite unforgiving. So let's try 100. No. Why it's becoming smaller and smaller? Maybe we can comment also this line here. So let me do some attempt, because without interactive plotting, this is a bit annoying. Nope. Even worse. Okay, maybe it's a bit too much. Or rather, let's make this. Okay. Maybe we can make a bigger slice. Okay, I think this is enough. I leave you the code visible. So basically, I'm just taking the first 1,000 lines, or you can do even a smaller crop, and then you can just replace the aspect value by automatic. So maybe it tunes itself. So I don't know how much you're familiar with the plotting. Also here, the origin lower means yeah, you have a question? The font, or okay, let's try. Is that okay? Okay. So basically, the plot values are aspects. It tunes how much the aspect ratio of your image. Origin lower means that the 0, pixel is bottom left. Color map gray, so we plot it in gray colors, and this Vmin Vmax is just a scaling of the color map. So usually, if you take the second and 98th percentile or something like that, it scales automatically to account for the whole dynamic range of the image. And then this one sets just the color bar horizontally to the bottom of the image. Axis off, remove the axis, and then you have just labels, and tight layout and show is just to make it a nice fit to the screen and plot it. I was just playing a bit with, I don't know, the size of the crop, so the slice, and aspect ratio is always a pain with matplotlib. So auto gives you, let's say, a good balance. Sometimes when you know, like, you have less pixels in one dimension, but they are big, it just compresses a bit the image. But this is a crop, so that's okay. No problem. So we can maybe try even a smaller crop. I just wanted to show you. Okay, so the thing here, you see the image is very, very fuzzy, very noisy, no? And you remember from this morning that this is because SAR is a coherent system. So basically, in each of these pixels, you see what the radar acquires given the antenna beam and then the aperture synthesis and the range pulse bandwidth. So everything that falls within the resolution cell, this function, let's say impulse response function of the radar, is summed coherently. So it means also the position inside the resolution cell of your scatterer matters. And You have a different, let's say, geometric combination according to what is in the scene and the way that you are acquiring. So that's why you see these salt and pepper noisy patterns over the images. So we can have maybe another look again at a bit in between size crop. Okay.
Wow, yes, so that's what we're finding.
So is everybody okay with that? Or okay, so we can go on. So how do we get rid of the noisiness? So as you saw this morning, we have multi-looking. Multi-looking is basically making some statistics. So we have the image. We basically need to average more pixels, no? And we average in particular the intensity of the image. So it means we are averaging the incoherent part because we have taken the absolute square value. And this is basically more or less equivalent at taking different portions of the image as seen by the antenna and average those, no? In this way, you get, let's say, a better statistical estimate of what you have in that precise location. So you reduce your noisiness and you should see a cleaner image, so a less fuzzy pattern. But at the same time, you're giving up resolution, no? Because you're averaging these different, let's say, portions of what the antenna has seen, or otherwise, looking at the other direction, the range 1 of your pulse bandwidth. So let's see this in practice. So the next cell basically tries to do the averaging with different number of looks. So let's say a bigger, progressively bigger averaging window. And you will have multiple plots and you will see the difference in between the various level of averaging. So basically it's just a very simple for loop in which you apply a function to this absolute square value of the HH image with different values of this window. Here we choose just a square window for the sake of showing the principle. So with increasing levels. And also here we don't care very much about the difference between resolution and pixel sampling, which is two different things. But the oversampling factor for biomass is quite small, so we roughly assume, just for showing this thing, that more or less we are averaging independent pixels. If it was not the case, so we need to account for that because let's say we can make the window also big, but if we don't average independent samples statistically, we're not having a gain in this sense, no? Better statistical estimation and cleanness of the image versus loss of resolution. Just since we are using this function, you can maybe for a while open this common function file. Besides some very basic imports, so we're interested in the first function, this filter down sample. So basically what it does, it computes just a template matrix, a filter window, which is made of ones, and has in range and azimuth R and X, the size of the window that we specify. Remember to use integer values when you do these things in Python, like initialize an array, otherwise it will give you an error because the data types is not, let's say, auto-tuning like in the MATLAB, for instance. This square window is a normalized template, so we want to normalize each value for the size of the window, which is the product of the two dimensions. And this is because basically we want to use a convolution function. So convolution is basically a way to smooth an image. I don't know how much you are familiar with that, but let's say you take your image, you take a template, a square boxcar window in this case, you sit on the first pixel, you make the average of all the pixels in the window, then that's your average for that pixel, then you move to the next pixel and you do the same. And you do this like over the whole image with this sliding window. And of course, since you are averaging, then your neighboring pixels will become dependent by the pixel nearby. So you can also downsample this a bit afterwards and save some space, some memory. No? And usually a safe choice is to downsample wisely, for instance, half the window length, so you're sure you're not throwing away information. So the reason this is normalized is because you want to do an average, right? So if you want to do an average, you sum up all the pixels and then you just divide by the size of the window. So basically you do just this. In this case, we use this FFT convolve. It's a function of SciPy. It is quite efficient. And it's more efficient than doing this in the time domain. So in the time domain, the process works like I said. So you have this sliding window, you compute the average, you move step by step. Instead, it's faster to do this in the frequency domain. So if you remember a bit the link, let's say, between the time representation and frequency representation, the signal processing mathematics tells you that if you do a convolution, which is this process of, let's say, sliding a window and averaging in the time domain, in the frequency domain, this is equivalent to a product of the spectra. So basically what this function does inside is that. So it transforms your data, does a product of the spectra, accounting for all the right things like padding your data, because otherwise you would have aliasing, and then gets back with an inverse Fourier transform in the time domain. But let's say for the sake of this practical, you just need to know this as a convolution, so this smoothing with a moving window. So the arguments of the function are your raster, your data, the filter window, and also the order of the arguments is important, so the filter window should go in the second place. And the mode same just tells the function to give you an output which has the same dimension of your original data, because the convolution, for how it works, gives you a result which is bigger than the data, because it accounts also for the border. I imagine when you are at the border, you are basically expanding a bit your data because you're using two data, actually, the data and the window. And then there is just a downsampling, or rather not. It depends if we need it or not. So let's go back to the practical. So let's run the cell as it is. The plotting function is just an annoying plotting function, so you, of course, won't go through that. So if you look at the output of the cell, and I'm sorry, maybe you will see that better on your screen, so you can zoom, hopefully, because, again, interactive plotting doesn't work. You see that if you compare the first one with increasing level of multi-looking, you have less and less noise, but the image becomes smoother and smoother because you start to lose detail. Maybe, I don't know if we can shrink the crop, or rather make it larger. So let's try again with this, which is bigger. Okay, so if you take a bigger portion, you see this better. And you also see it by zooming on very fine details, but let's say for now, I just stick with these because it's clearer. So you see, these are mountains with, I don't know, maybe some settlement, some city. And if you go from a smaller multi-look to higher multi-look, it becomes less noisy but more fuzzy. I guess you see that better on your screens. And so it's a trade-off. Huh? It depends on what you want to do. So if it's, even if it's for visualization, it depends on the details you're looking for. And tomorrow we will have a focus on this concept also from a more statistical point of view. So we can get back to this. And of course, if you have questions, interrupt me. Any kind, whether it's well, SAR, of course, but also lines of code not working or something you want to try.
I have one question. The sampling
Yes.
that you said at the beginning are then just coming also from the metadata, or just because you know those are the right sampling steps?
Usually the sampling step is annotated in the data. So if you remember the folder structure I presented at the beginning, you have in the annotation folder, there's one XML. It has a lot of information inside. I think the sampling step is actually given for biomass in a couple of versions. So usually for satellites you have a sampling step which is given in seconds. So it's a time dimension. And this is because time dimension is the acquisition dimension of the radar, no? So if you usually, let's say, or with other sensors, if you want to have this in meters, you'd have to scale it yourself. Which means in range this goes with the speed of light, half of speed of light. And in azimuth instead you have platform velocity, no? Let's say it is often customary to assume an average value, let's say, but actually it changes because the orbit moves. So your and also velocity on the orbit is different from that on ground. So, but you can compute that because you also have all the orbit annotated and also the velocity vectors of the orbit. For biomass, I think it's already given also in meters. It's at least baseline values, which is this 6.7 for the azimuth, which has 8 meters resolution or so. And 19 something for the range, which is 25 meters resolution. Maybe this also changes a bit. Well, maybe the sampling, no. Actually, the resolution, sorry, changes a bit with acquisition mode, the SWOT. Okay. So, any other question or even features that raise your interest, doubts? Yes, please. No, well, actually, let's say you can also sound coherently, but it's two different things. Here we're just focusing on the intensity. Actually, also if you average a complex cell, you reduce the resolution. Yeah, that's right. But the incoherent average is just, let's say, you reduce the resolution, you don't gain about the how much the image is definite, is sharp, let's say, no, visible visually. So you don't see this gain in reducing the noise. But we will have a part tomorrow which goes exactly into this detail and explains also you the statistics. So looking at the histogram and the distribution of the image in the case of no multi-looking and multi-looking. Let's say for now it is important because I want you to visualize the concept that you reduce the noise, and especially also for the tomographic part. This will make things clearer and more visible. No? Okay, other questions? Okay, yes?
You said it was a trade-off of the window for the multi-look. In our purposes, we pick which one to pick is the best for our purposes?
It depends on what you want to do. Let's say if you want to look at the overall mountain, you'd go maybe for a bigger multi-look. If you want to focus on the feature, you see when you increase the looks, you start to lose a lot. And then it depends, in fact, it depends very much on, let's say, yeah, it's still this trade-off. Let's say we will see tomorrow. Like if you think of tomography, like you want to estimate something at a certain spatial scale. Like for instance, imagine you want to estimate, I don't know, the top canopy, the profile of the top canopy on a tomogram. So you have to multi-look because otherwise this is very noisy and unreliable. If you multi-look too much, you'll have information of the top canopy at, I don't know, 100 meters, kilometers. So if you want to do a top canopy model, profile of the canopy height at final resolution, then you're losing. And usually the target is driven by the application. No? So if you know you want to deliver an information at a certain resolution, then you try to stick with that more or less. And then you can, I don't know, play games like I average more in azimuth rather than in range because range is already coarser, stuff like that. So it really depends on the application. There's no universal, let's say, answer. Besides, if you take single look, it's usually not very good for applications because you don't have statistical consistency. So there is a lot of theory about this. Usually the rule of thumb is at least you have to average 4 independent samples, which is really too few. Let's say from 9, 10 onwards, you start to gain. So 25 may be already a good number to the minimum. Then for some applications, you want actually to average 100 maybe, because it also depends on, again, on what you want to see, because instead, if you want to estimate atmospheric patterns, which I'm sure you know of, you can go to a bigger scale, because if you know your process as a scale of kilometers, then it's no use giving up looks. No? You'd be interested in averaging more and more up to the scale that you want to preserve.
Just so I understand, what is the difference between using multi-looking and just taking a Gaussian or other moving window filter?
No. You can also change the window shape. So you mean like using a Gaussian function instead of a boxcar?
I think I don't understand yet the concept of multi-looking.
Okay. Well, the point is to average more samples of your image, provided that they are independent. So let's say ideally that they are sampled at the resolution. And then you reduce noise, this kind of physical noise, which is speckle in particular, to gain some better estimation of the pixel. In this case, it's reflectivity, or rather intensity. If you do that on complex data, it also amounts to the phase. So also you are estimating a better phase, let's say, for that pixel. So it's just a statistical thing. No, you can avoid downsampling, actually. Averaging, you have to do. Downsampling, you can avoid. It depends on how much storage you have and what you want to do. Well, let's say if you can keep all the samples, maybe it's better not to downsample. But then you'll have to remember that neighbor pixels will be dependent from each other. So they will not be independent anymore up to the averaging window. So your next independent windows will be in well, here it is look. So let's say we do 5 meters, 100 meters. It will be 5 meters, 100 meters. So downsampling is basically a matter of saving some storage. But usually what I do, I don't downsample at the resolution because it's a bit dangerous. No? So let's say maybe we don't have time to go in details here. But if you think of a function like, I don't know, even a sinusoid. If you sample at the resolution, you'd go from peak to peak. And for you, digitally, this is a constant. So because it's just 2 samples. If you want to see the sinusoid, you have to sample more. So it's a bit dangerous to sample at the resolution. Usually, you always have a margin factor. And in my opinion, a margin factor of 2 is good because it gives you enough samples. Also to better visualize the image because it has more continuity. It's not blocky, let's say. So we are at a cell where we compute the multi-look for the whole image. You can just run it, I guess. It's same theory as before. And now you have the whole image, HH intensity, multi-looked for the whole area. And I suggest you compare with the optical area below. So the plotting was supposed to be interactive, and in theory, you could zoom. Unfortunately, it doesn't work. But let's say maybe since we are a bit tight with time, we can skip the zooming. And I prepared just some questions for you. No? So look at your screens, and can anybody tell where the SAR sign, where the SAR is flying, and where is it looking? Anybody? Come on, don't be shy. But look at you. Hmm? From the south. From the south? So where is south? No, I'm deliberately putting you in a bad position. But so if you have to say north, south, east, west, what would you say? Which is north, south?
From south to north. So it seems that the mountains are bending our ways.
Yeah, this is a good point. But then would you say then it's north, south?
No, I'm not sure it's north south.
So think how a satellite flies. No? How's the orbit usually?
North south south.
Exactly. But then what you said relates more to maybe another point. So the fact that the mountains are a bit, yeah, but so if it's flying north-south, so the radar looks to the side.
Yeah. So east west.
Yeah. So again, so yeah. So north-south or north-south?
Yeah, no, up down. If it's north of Alps, it's looking east west.
Yeah, exactly. So again, what is north-south here?
North
Horizontal or vertical?
is horizontal.
Yes, yes, that's correct. So actually, if you don't know how it's flying, which is north and which is where it's looking, which is north and which is south, it's hard to tell, and we don't need to name it here. But yes, north-south is horizontal, and east-west is vertical. And it's because you see the mountains are all slanted, no? So you saw this morning, so we are side-looking, and so everything is distorted. And actually, I don't remember if you touched the point in the morning because I could not attend that particular point, but have you spoken about layover, foreshortening and these kind of things? No? Okay, so maybe I can tell you. So basically mountains are compressed. So what happens, I guess you better look at your screens, but you will see bright areas like this one because the side of the mountain is compressed, so in your resolution cell you have a lot of stuff happening, no? And this is why it's very bright. And then this gets to a point, you see it maybe here in the middle of the image, where actually the mountain gets also reversed. Why? Because the top of the mountain is closer to your sensor, no? And since you are locating based on distances, the top of the mountain is actually nearer than the bottom. So, and this can actually mask also some pixels because you see that the face of the mountain towards you, which is reversed to the other side. And also on top, you'll see darker areas. This is called the shadow. And it's because the radar sees the top of the mountain, but what's on the other side and cannot be reached by the ray is not imaged. So you have actually lack of signal there. And also, still look at your screens, which is nicer, I guess, like here, maybe here. You see dark features. What is that? Anybody? So what a dark and narrow target could be?
Intensity of the reflection.
No. This is intensity. It's the whole image, but I'm saying like look at maybe in your screen this streamy dark area here.
Because radar didn't see the whole.
Yeah, there is a lack of signal. That's correct. But what it is? So water, because well, actually, if you look at more and more biomass images, water will be a surprise. But let's say ideally, often you have a specular refraction, so you don't get a return from your radar, and that's why it is dark. So you have no signal. And what is that instead? Yeah, you have a lot of bright points, all localized in the same area. You'll see also those here and there. There are a lot of settlements, of course, but that's a big city. That's a big city of Nagoya. Okay, so I'm just skipping over because we have not much time. So you see also the optical image is not, so it's wider than the SAR. If you play the exercise, it's more or less this area here. So, but I put it wider also for you to have a look. Also, you can go back later, look how the mountains look in an optical image compared to how they look in a SAR image. No? But we already talked about this, so this difference in geometry. And okay, so polarimetry, just a flash. You've seen this morning colors should be informative of different scattering, no? Different physics. So I just don't go into details because I know on Wednesday, I think, and Thursday you'll have much more from Costas, Irena, and Armando. But let's just play this cell. This cell here basically takes the three intensities, multi-looks a bit. Multi-looking is also to enhance a bit visibility. And then computes what is called the Pauli composite. So basically, the three channels that are computed here, it's a combination of the polarizations. They are mapped to different layers of an RGB image to reflect this different physical coding. And if you play this cell, let's do that. So it takes a little while. You see a completely different picture, very colorful and very informative. So anybody feel like saying who's who? Or rather, again, we have the city, we have the mountains. So the mountains are very green because probably more volume scattering is happening there. So you have forest, you have vegetation. The city is very much red. So lots of buildings might be aligned with the flying direction of the radar. So you have this double bounce effect against the facade of the buildings. And they get purple because it's the combination of polarizations that highlights the best this kind of mechanism. Water may look dark or not. Here it looks dark. In other biomass images, you will see more colorful pictures because at P-band, which is a 70 centimeters wavelength, if you have waves and crests on the sea, they may generate a scattering. Yeah? So it's not just specular reflection. And then you have other cities or settlements here and there. So you see it's not completely green. Okay, do you have any question about this? Or,
why is the color kind of brighter in the south? Is it just
brighter here? It's still because of that, because of these geometric effects you get. Also, it depends very much on maybe how it look bright or not in colors, how you scale the colors. No? And let's say, but I leave this to the PulSAR guys then in the next days. The scaling is a bit of an intuitive way of seeing the scattering mechanism, so it's not something exact. No? And actually there are different ways to scale. Different people scale in different way, but usually when you want to show the added value of polarimetry, you try to find the scaling highlighting this kind of difference in mechanisms. And then, of course, after that, there are the compositions, which are more exact, let's say precise, but that's not also you will hear in the next days. Okay? Very good. And okay, so I guess given the time, maybe we can carry on to the second part. So now you'd need the SAR TomoSAR part 2. I just opened a different files because we had some technical issues this morning, so I renamed mine, but for you it's SAR TomoSAR part 2. And this is tomography. So you'll have to play the same game of changing the paths to the share bucket files. So I give you just a couple of minutes for you to change this, and then we can start. And it's the same as before. It's just different files, of course, but let's say the path up to the folder is the same. can you please maybe raise hand when you're okay? So I know you can start, we can start. Okay, okay. What about there? You guys in the bottom row are okay? Okay. So let's start. Again, I advise you to cancel these lines, and this is already uncommented for me, but you can do the same. So let's just keep, or rather run the imports and the loading. The loading will take a little while more because it's actually a lot more stuff. So this time we have 3 stacks, full polarimetry. It's 6 images. You find also a link at the top of the notebook. There's a nice web story that was shown this morning about how this dataset was processed. It's a mountain national park, so forest in Brazil. And you also have a lot of information more. So you have well, access, then phases and calibration phases. We'll see in a while, but we go more into deep tomorrow. So I will just go very fast on that. You have the INSAR wave numbers. So for each image and each pixel, you have a number that converts your height to a phase. And this is needed to compute the tomographic focusing. We will review this later. And then you have some more information like the incidence angle, range slopes, and digital elevation model. And you can also then go back and read later at the top of the notebook. So the first cell, if you run it, basically just prints some information to the screen. Average INSAR wave numbers, so basically it's for each image the average number. So if you look at the actual maps, you see that it doesn't change very much, this value over the SWOT, but a little bit because it depends on the viewing geometry, which changes from point to point. You see it's not 100%, but quite a regular progression. So you have, let's say, ideally an even sampling in the orbital patterns to have the different views in elevation that you'll need to do tomography. You also have a print of the average incidence angle. Here I just averaged in azimuth and printed out 3 values in range just to show you that it increases going from near to far range, so from left to right. Doesn't change much, so between 27.5 and 30 degrees and a half. And then you have a plot of the DEM. So this time with axis, range and azimuth. It's actually kilometers, and it's kilometers including the nearest distance of the sensor, which is to the bottom left. And the ground range slope, which is annotated in the data. So it means you have the actual digital elevation model and the slope just in the range direction. Actually, this is informative because you see, so this is a mountain national park, so you have a lot of morphological features. Also the fractal patterns may be rivers or even valleys. I don't know exactly. And then you have also, you see from this DEM, quite some trend in azimuth, or rather a shift in between 2 areas, which we will see bring some effect to the tomography. And the range slope, of course, you have also the range slope, but it's something very local for this scenario. So on average, you see it's 0 with some tilting of the mountain terrain. Okay, so there's a little primer here. Let's not go too much into the details, but let's say the data usually come with some additional lookup table that are needed to process them correctly. Maybe we can get back to this point tomorrow, as we will have the interferometer practical, but basically if you take the phase of an SLC, it usually has a big contribution from the nominal geometry. So all the stack is processed with respect to a digital elevation model. Let's say you have an average phase center, so the distance for each point from the sensor to the phase center of the scene. And then you have then a contribution that you can express like this. So the relative height with respect to the DEM. So in this case, you can assume DEM is the 0 level. And then you have differential height with respect to that, which is scaled by the wave number. And then you have another term, which is disturbance, because usually the data have also nuisance factor in the phase, for instance, ionosphere. So if you get level 1C data from the map, ideally they should have some lookup tables that allow you to compensate for this and for this. So you can basically retune the phase level to the DEM level, but also remove the disturbances. Otherwise, you'd have badly focused images. And in this case, you end up with this. So doing tomography means measuring the relative height level, no? Which actually, in this case, it's not with respect to DEM, because the lookup tables that are inside the data also compensate the difference between DEM and DTM. And this is important because like DMs available usually refer to height level which is not the one of the ground. So it means like if it was taken with a higher frequency SAR, for instance, it would be referred to the canopy level, no? So if you are going to do tomography just with respect to this level, assuming that you have removed the disturbances, your 0 would be on the canopy level, no? But the phase screens that are annotated allow you to set the ground, the phase level on ground. So as Stefano said this morning, when we're going to do tomography, we will see 0 on ground and the image relative to the ground in height. So I can get that this may not be straightforward right now, but we will go into more detail later. And also the lesson that it's going to happen after this practical is about INSAR. So I should touch some of these points. So this cell is simply the application of this calibration and tuning phases to the data so that we can actually compute the tomography. And just for the sake of seeing the difference, we are also storing a copy of the HH stack to try to do tomography also on uncalibrated data to see what's the difference. And then tomography is just like it was presented to you this morning. So you have this stack of SLCs, which are now calibrated and retuned in phase, such that if you compute a tomogram, the ground is at 0. And then you basically apply a phase shift, a phase term, which is dependent on the pixel, of course, on the INSAR wave number, which changes from point to point and depends on the geometry of the sensor and of the scene. And then you can put a height value in there. So ideally, you can try to compute tomography for all height values, no? Ground, 50 meters above ground, 30 meters above ground. And then once you have done this rephasing, of course you have to do, let's say, a rephasing for each height value that you want, because this is given from annotations. These are calibrated. Each pixel has its value. This is each single height that you want to compute. So you apply rephasing for each different height, and then you sum coherently the data stack. And usually there's also a normalization factor, which depends on the number of acquisitions, but it's not really important here. The important thing is the concept of rephasing and then coherent sum. And then, okay, maybe we don't have a look at the single look and multi-look tomography because time is short, but let's say bear with me, and from what we saw in the previous part, also here, once you have computed the tomography, you have to up-square and multi-look a bit, because otherwise it would be very, very noisy, what comes out. So, okay, we can run this cell. It should be not so lengthy. Basically, what we are doing in this cell is exactly what we said. So here, let's say for each polarization, we take the stack and we do this coherent summation after having applied what we call the steering matrix, so the complex exponential factor, which is the rephasing. And in a case we want to do ground tomography, so to take a slice at 0 level horizontally, this is simply 1, because we can put 0 no, as an height. So it's just a coherent summation of the calibrated stack. We do this for all polarizations. And also we want to compute tomography at canopy level. So imagine we are taking a slice at ground level, horizontally, and a slice at 30 meters, let's say. We saw that this is, let's say, an height, which is very informative of what's happening at canopy level. And so it's as simple as that, you see, just a product and a summation along the third axis. So the images are range, azimuth, number of images. So we sum along the stack. And we also do this for the uncalibrated one, no? So, and we'll see maybe in the next cell or so what happens in 2 cases. And once we have done this, the last lines of code are basically just some multi-looking. So once we have done this, for each polarization, we have an horizontal slice, 1 for ground, 1 for canopy, 1 for each polarization. So we have 6 images in total. Dimensions, range per azimuth, no? Because we have done this for 1 height level and the summing along the stack. So a nice thing to have, okay, if you run the cell afterwards, is because if you look at a single slice, let's say it's radiometry intensity, but it might be informative or not. So since we have computed a tomographic slice, both for the ground and for the canopy, we can actually compute the ratio of the two, no? And put it in a logarithmic scale. So we can compute kind of for each pixel a ground to canopy ratio. So we can see for each pixel and each polarization, this we can do for each polarization, how much is the contribution of the ground and how much is the contribution of the canopy. And if you look at the images, it actually tells you something. They don't fit the screen altogether, maybe. So let's try zooming out a bit. So you see that polarization bears some kind of information, no? Because, so these are put in the same scale, same dB scale. Don't look at the absolute values, but rather at relative intensities, no, of the ratios. So you see it's bluish at VH, and it gets brighter at VV and HH. You need, yeah, needs you. And so polarization gives you different sensitivity to the scattering mechanism. It means that since this is a ground to canopy ratio, that at VH, the cross polarization, we are sensing less ground and more canopy, and that's why it's bluish. And we are sensing more ground actually at HH and VV. And if you look closer, actually HH senses the ground the most, because you see, especially here in correspondence of the features of the rivers, the valleys, whatever they are, it's more reddish, but also overall, you see the pattern is a bit more reddish than this one, which is more greenish. So you will see in the next days that indeed polarization paired to interferometry also is really a powerful tool, because the scattering is physical and you can map these by using different combinations of polarizations. Okay, so you can also compare here, it computes the Pauli composite, just like the previous practical, for the single look images. No? It means this is not tomographic, it's just a composition of the polarimetric channels for the single image. And you see that colors are quite complex here, because there's a lot of green, because a single image has everything that you sense in your pixel in elevation. A bit limited by the antenna beam, but you sense a lot. Let's say you don't have a resolution vertically. So you have the green because you sense the forest, but you also have a lot of reds here and there, all over the image. And the reds are more red in correspondence of the valleys or the rivers, so where there's less vegetation. But if you also compare this with the ratios that we have computed, you see it's harder to distinguish things here, because the colors are more mixed. Whereas if you compute something from tomography, you have a better way of discriminating based on the polarization combination that you choose, who's ground and who's canopy. Okay, the next cell is basically a visualization of the 30-meter slice, so let's say the one of the canopy, in case of calibrated and uncalibrated data for one polarization. So it's just an example. So you see from this image that in the case of calibrated data, you have a lot of backscatter, so the map is more red. So it means that we're actually having signal from the tomography at 30 meters. In the case of the uncalibrated data, instead, you have a fuzzier pattern. No? You have less, because this is not calibrated, so the numbers just sum up randomly, and you don't get a focus image. Actually, maybe we can look at it again tomorrow at vertical slices. If we do that, you see that in one case you have a focused forest, so you can see a profile. Otherwise, you see something blurry, like all mixed. So you cannot distinguish the forest anymore. And okay, the last cell is basically tomography. It takes just a little time, not much. But this time we look at something, I hope. Disappeared again. Ok. Sono quasi alla fine. So if you look at the code, which we don't have a lot of time to do now, it's basically computing tomography, but for vertical slices. But it's not a big deal because this is also a topic of tomorrow. So let's say for now, bear a little with me, and then we'll revise this tomorrow again. So it's computing tomography and again doing multi-looking. Sono alla fine. Non lo so, questo devi chiedere a lui.
Okay, perfect. Thank you.
Okay. So you can also run the last cell, which is plotting. And here we are. So this is a vertical slice for a constant range, which is basically mid-scene. So if you look at the DM or the map, imagine you slice at mid-scene for the three polarizations. And it's quite interesting because, first of all, we see, like here, if you look at the DM, for instance, but also the horizontal tomographic slices, this is where the river, the valley, whatever it is, no? So in some cases you see there's no signal, in some cases you see a very bright signal. So it may be there's some complex scattering there, no? Some even multiple reflection or so. But even before, actually you see, well, you have to have maybe a little imagination, but this is a forest because you see in this area we have trees which span from 40 to 60 meters height. So you see the bottom of the tomogram is at 0, and the top goes actually at this level. It would have been nice to have validation data like a laser scanner model of the top canopy here. Unfortunately, we don't. But otherwise, you would see something like this, following the profile of the tomogram. And another interesting thing is you see that the scattering changes in between the polarizations. So this is the image of the same slice in 3 different polarizations. So look at the brightness of the tomogram. So where you have more scattering is red. No? You remember from this morning. So HH, look where the scattering is. Then start looking at HV, you see gets a little higher. And then VH, it's the highest, no? And why? Again, because if you think also the previous plot, horizontal slices, ratio ground to canopy, VH senses volume the most, HH senses ground the most, and VV is a little bit in between, more towards HH maybe. And also the scale is different, no? So these are computed with the same scaling factors. So you see there's more signal here, slightly less here, quite some less here. And also another interesting feature is this is a slice of the DEM for this corresponding to the tomograms. It's a bit noisy because probably the DEM is unfiltered, but look at the low pass trend, let's say at the overall trend. You see there's a change in elevation, then quite a shift, and then some more shifts and movements. And you see maybe this looks better in your screens. If you look at the top canopy, or rather at the behavior of the tomogram, it follows this a little, no? Like here it gets a bit higher, you see the DEM, like here, here, and then where you have the shift, it goes down. And this is why basically when the data are calibrated, you set the phase level for one height, let's say for one phase center, but then it means that you're just fixing one point in your cell. You remember you have a resolution cell, so imagine you have like a slanted terrain going like this. You have many scatterers which are not the same response. Maybe you have brighter scatterers here, and you have set the phase level at 0 here. So the tomogram goes a bit higher because your phase center then is driven by the strongest points that are on the top of the slope. Yeah, okay, fantastic, bravissimo. That's it.
You're actually measuring this height.
Yeah, exactly. So you sense this, and that's why your tomogram gets a little bit higher.
And the opposite here, you're measuring it's much smaller than the actual height of the tree.
Yeah, that's it. So I don't know if I should stop.
Yes, I will,
so maybe if you have some quick question, then or otherwise I leave to Laurent. I know this was a bit compressed, sorry about that. So we have had some issues with the setup, but let's say good thing is, well, you can have a look because you have the materials, but we also get back to tomography tomorrow in a slightly different way, but not so far. So we can go more into deep tomorrow.
perfect.
Okay, thanks a lot.